Hello, this is Tommy. Welcome back to genomics. So in today's video, I'm going to show you a very useful function called tile from the genomics ranges package. So what does tile do? So you can type the question mark tile to get the help page. So it's from the genomics ranges package. And you can see tile actually will truncate your genomic ranges into, for example, the same length of beans. And why this is useful, for example, like in single-cell ATACseq data, you have the whole genome and you can actually tile the whole genome into the same length of beans, for example, 1 kb or 2 kb. Then you can count the single-cell ATACseq number of reads in those beans. And then you can use the count matrix for each cell and for the whole genome as a count matrix and use that as a clustering matrix to cluster different cell types, for example. And this actually can be very useful. Okay, and a very closely related function is called sliding windows. So instead of actually truncate the genomic ranges or genomic regions into non-overlapping beans, in this case, it will be actually overlapping. So for example, you have this is your full genomics ranges regions, and then you can, okay, let's have a sliding window of 5 base pair, for example, 5 base pair. This is the first, and then you have maybe you have to actually define the step. It's like 1 base pair or 2 base pair. So then you actually slide the window, then same 5 base pair, but 1 base pair just sliding to the next base pair, then you go ahead sliding. So this actually creates actually overlapping windows. Sometimes you use that to actually to smooth the signals for particular genomic regions. Get to see how to use that function, let's go with some practical examples. So first, load libraries here. Genomic ranges calculator. This is used to import, for example, bat tools from a file. Import bat files from a file. So dplyr, readr, those are for reading and wrangling data frames. Okay, so let's create the genomic ranges. It's a dummy one, so if you look at it, so those are different chromosome names and ranges like 1 to 11, 2 to 11. Okay, and let's see how it looks like if we use the tile function. So you can use tile, and then you can give it the genomic ranges, and then you can do either width. So this will determine, okay, each bean will be 2 base pair long, right? Or you can use n, for example, you want to truncate each genomic ranges to how many beans, for example. So in this case, I want to split every range to a 2 base pair beans. So if we do that and take a look, so it returns a genomics range list object. So each of the genomic range, so each region here will become the entry of the genomic range list object. Okay, and you see here, this actually becomes this whole thing. 1 to 11 will becomes like the six actually different genomic beans, and the width is 2 as we specified here. And remember, R is 1 base, so to get the length of the genomic ranges, so you use end minus start and plus 1. Okay, so this is a length of 2, for example. They're all lengths of 2, and did you see here? So then you can just use unlist function to turn it back to a genomic ranges object. Then it will collapse all of them into a single genomic ranges object. So let's take a look at a different example. So in this case, we can use the ATAClayer package function to read in the file. Okay, so look at, so this is the dummy genomic ranges object. So chromosome 1, 2 to 14, 15 to 20, and 31 to 38. Now let's define the bin size to 5. And we can actually take a look at the width of each genomic region here. So just use the width function and it will give you the length of each region here. So if you do that, take a look. So it's a 13 base pair, 6 and 8. And you can see here 14 minus 2, 12 plus 1, so that's 13. Okay, then this is 6 and this is 8. And for example, if you only have like 13 base pair, if you have 5 base pair per bean, the last bean will be only 3 base pairs. And so that's usually how it works. So the last bean will be partial. So if it's not full bean size. So, but we can use the ceiling function to get the number of beans, right? For example, if you use this, for example, let's do this. So then the first will have 3 beans because 5 base per bean, and this have 2 beans because 5 base pair, then you have 1 base left, and similarly for 8. So this is the bean number. So what we can do, actually, you can resize the bean, the original genomic regions, to the full size. For example, you can do here resize, and genomic ranges can fix this is use the center, so it will be the center of 2 to 14 here, or you can fix with start or fix with end depending on the needs. And then the width now will be the full size, like bean number times the bean size. For example, like if you have 3 bean here and 5 base pair per bean, so this one will be extended to 15, and this will be extended to 10, and this one will be extended to 10, right? Based on the width, the total width. So you can do the resize. And now if you look at the resize the genomic range, now it's 1 to 15, 13 to 22, 30 to 39. So this 10 base pair long, 10 base pair long, and this 15 base pair long. So now you can actually resize, tile the genomic ranges with width equals to 5 base pair, right? And then you can, so now you have 2 beans here, 2 beans here, and the 3 beans for the first. And then you can do the unlist as well, right? But as you can see, now they are actually overlapping with each other. For example, 1 to 5, 6 to 10, those are non-overlapping beans. But 11 to 15, then you have this bean. 13 to 17, this one actually overlap with this one, right? So what you can do, you can actually, before you do the tiling, this GR center here, because this one, you have the overlapping one, 15 here, 13 here, so those two are overlapping with each other. So you can use the reduce function and to remove the, so essentially to remove that overlapping thing. So if you use the reduce function, take a look at here, now actually it becomes 1 to 22 and 30 to 39. Those are non-overlapping, genomic regions. Now you can do the tile function again, use the same width, and take a look. And now you get the non-overlapping 5 base pair per bean, right? So it just shows you like you can do actually many things. It really depends on the needs of your analysis. And as I mentioned in the beginning of the video, a very commonly relevant function is called tile genome. So you can actually tile the whole genome actually from the chromosome start and to the chromosome end, and then tile them into the same length of beans. Then you can calculate whatever statistics you want in those beans. For example, even GC contents, a number of reads in those regions, right? So let me show you how to do that. So you can, so in this case, you load this transcription database object for HG38 human, and then take a look. So if you take a look, TXDB is a TXDB object. So what you can do, you can use the info function. It will give you essentially the info object, but it will tell you actually the chromosome and the length, and you can directly put that into the tile genome function And then you say, okay, tile width will be 10,000 base pair per bin, and then here, cut the last tile in chromosome 2. Okay, so this, if you do this, now you have actually for every chromosome, now you have this 10 kb bins. Okay, and then you can do some interesting things with those bins. Okay, so that's it for today. I hope this little function can help you in your data analysis. Happy learning. I will see you next time.